So test is on Thursday. It'll be, I say, through chapter 2, but we'll do 2.11 today, Lagrange multipliers, but I probably won't put one of those on the test where you have to do it using Lagrange multipliers, because what we'll find is it's a second way of doing it as opposed to the method in 2.10. So if you want, you can think of it as through section 2.10 in chapter 2. So we'll start 2.11 today, probably. And then tomorrow we'll start integrals. So we'll be going into chapter 3. Later today, so just pretty much after class, depending on when I remember, I'll put up a review for the test. And that's mostly what we're going to do on Wednesday, is just go over questions on it. I will put up the answers on Blackboard tomorrow, so you'll have the answers going into class. Sort of more like office hours. A little bit. Usually I would say you can have a page of notes for the test, but like the quizzes, it's pretty much open. Like the quizzes, even if you're thinking of this as open notes, you should write a page of notes, because now that we have more material, if you try going through all your notes, you won't have time to finish the test. The test will hopefully be made to take hour 15 minutes, because longer than a usual semester, but not the full time. And then you have the full time for the actual test, plus 5 or 10 minutes on either side, so up to maybe an hour, so somewhere between an hour and 40, an hour 50 minutes. So hopefully it'll be made to take about an hour and 15, 20 minutes, and then you have the leeway at the end. So in some ways, looking at past tests, I have obviously tests for the last few semesters. The one that's going to look most like what you'll see Thursday is the one from last summer. That was made for an hour and 40-minute classes, whereas the fall and the spring were made for 65-minute classes. Also looking forward, this is now how it's going to work for the rest of the semester, which is last week we had a quiz, this week we have a test. Next week we'll have a quiz, in 2 weeks we'll have a second test, then we'll have a quiz, and then we'll have a test. The only little thing is, instead of Thursday, it will probably be the day of the final. So instead of a final, we have the 3 tests and the 4 quizzes. We are in 2.7, so let's do 1 or 2 of those. So the usual things, start with homework. So we did this, but I left off the quiz to keep it separate, because we have the 2 ways now of getting tangent lines. One is if we're given a function, and one if we're looking at a level curve. As I said at the beginning, that's kind of the difference between having an explicit function and an implicit function, and I'll sort of do that with here also. In either case, though, we do start the same way, which is we get the gradient. So here the gradient is that in general. .7. Oh, that's a 7, yes. Sorry about that. Usually it makes my 3s look like that, but this one really is a 7. And so if I put in 0, 1, I get 1, 2. In this case, unlike what was a quiz, you don't have to put it in 0, 1. I'll remind you in a second. And that is, so this is all the information we need. What is the tangent line we get? pretty much just like the tangent plane, just the 0 is equal to 1 times x minus 0 plus 2 times y minus 1. And so the way to think about this is when we say get the level curve, what we're saying is what we're going to do is we're going to plug in the point that gives us the value and then set the function equal to that. So we don't need it here, but to sort of explain what's sort of going on, let me put in 0, 1, not that we need it. I put 0, 1 into the function, I get 1. So we're looking at, here's the level curve. I should circle that because that's our answer. There's our level curve. And what we want to do is get the tangent line to this. So one way of doing it is we can make this explicit. I could, for example, solve for y in terms of x, say y is equal to plus or minus the square root of 1 minus sine of x. Take the derivative and use the stuff from before, or doing it implicitly here. And so you can see the reason we don't have to worry about the 1 is when we take the derivative of 1, of course, is going to be 0. So if we take derivatives implicitly with respect to x, that 1's going to go away. So here's the one version. Any questions on this? If I didn't leave the level curve, so if I just said find the tangent plane at the point 0, 1, then I would still get the gradient, but then I would use the 1, and then I would use something like z is equal to 1 plus 1 times x minus 2 times y minus 1, which gives us the extra dimension to make it a plane instead of a line. Right. So the 1 squared plus sine is the level curve through the point 0, 1. So this is the thing that they actually ask for in the text, which is get the tangent line. And then this is the level curve that we're looking at the bottom. They also ask, and I've told you this before, but I should remind you every once in a while, they also ask you to graph it and show the tangent line on the level curve, but you don't have to do that. Any other questions? Oh, I didn't say this is, now that I'm erasing, you don't really need it. That was problem 12. Sorry about that. So let me just do one more. There's pretty much that's the idea for it. It's just that here we get a tangent line. And here's tangent. The only difference is now we have one extra variable with tangent plane instead of a tangent. Level curve is saying that if I plugged in the 1, 2, 3, I get a number, in this case 13, 14, and then I fix it, which gets rid of the one dimension. Whereas if we did it using the previous actions, where we got the value of f and said w is equal to, then we had a 4-dimensional surface. So again, like most of the stuff from this chapter, take the gradient, plug in the point, and again, we don't have to put in the value. And again, essentially what we're doing is we're putting in the point 1, 2, 3, which gives 14, and that's our equation that we're looking at to get the tangent plane. 14 is equal to x squared plus y squared plus z squared. So the only difference is, as I said, there's one more. And really, you can go as many dimensions as you want. It just gets a little weird. So in that case, you make it a tangent set. So it's x squared plus y squared plus z squared plus w squared. And it'd be a 4-dimensional thing. So those are the only two I want to look at from 2.7. Any others that you want to look at? We already looked at one last week. Right, so it's not z equals. Well, if it would be using z, something like, so let me put next to it kind of the two questions. So here we find the tangent plane to the level curve. If I just said find the tangent set at the point, so find the tangent set for the function, then you would start off the same way, but then you would put in point and get 14, and then you would get something like that, 14 plus 2x minus 1. Oh, do I say, well, level curve, level set, yeah, whichever one you want to use. So in either case, the level whatever is telling you that extra variable. We're fixing the function, which means we're getting rid of a variable. Whereas if we just said get the tangent set at the point for the function, we're not setting it, and therefore we're keeping that extra dimension. So the level curve, level set will tell you that we're losing a dimension. And that means we're going to be using this type of formula, which is 2.7, compared to this type of formula, which I forget, 2.5. So those are the two differences. Okay, so any questions on the difference between the two? And one last chance. Any other ones from 2.7 that you have questions on? Okay, so let's look at one or two from 2.9. So look at 4. There really aren't many. I'll do a couple. And they also kind of split it up. I forget what the other problem is, but it's something like 4 is just find the critical points, and then something like 10 is then say whether they're minimums, maximums, or saddle points. So I'll just do them together. So find and classify critical values, 4 points. So as we did last week, it's the extension of Calc 1, which is you take the derivative. Here there are 2. Set them equal to 0. And then figure out what points will make both the equations equal to 0 at the same point. And so this one is somewhat similar to the one we did on Thursday, I think. So the easiest way to do it is to solve for one and then plug into the other. So here I'm not sure which one's better. We can use the second one to get y is equal to negative 1/2 x squared, plug in into the other one, or we could do do this out. So it should always work for either one, but one might be a lot simpler than the other. So I'm going to use this first one. So that's equal to 0 if either x is equal to 0 or y is equal to -1. And then plug that into the second equation. So if I plug in x equals 0, I get 2y is equal to 0, which gives me y is equal to 0, which gives me the one critical point. If I plug in y equals -1, it gives me -2 plus x squared. So x squared is equal to 2. So what we need is that each equation is equal to 0. So this equation is equal to 0 if x is equal to 0. So if x is equal to 0, that's 0, right? If y is equal to -1, it's 0. So I don't need both. I just need one of them to be true to make the equation 0. And then plug into the second one to make the second equation. So in some ways, very much like factoring x minus 1, where it works either x is 0 or x is 1. Similar idea. Which is plus 2, so we get 2. Let me stop here for a second. Let me stop. Is this better or